Determination of external forces, infinite element nodes in the Mathcad. This is article number 4.11 of the book Mechanical Systems Calculations of the Marine Facilities. So we consider the exercise. The exercise consists the 6 lessons. The first lesson we did in the article 4.10. It was the set of the initial data of the geometry of the forces concentrated, acted on the statically definable frame. This is the second one lesson, the determination of the external forces in finite element nodes in the Mathcad. The vector of the external load reduced nodes of the discrete model is determined as the sum of the vectors of the external load from the concentrated forces F stroke applied to the nodes and the concentrated forces Q, to which the distributed load acting on the rod in finite element is reduced. So together, the vector of the external load we can find is the total of the F stroke plus Q. F stroke is the assigned vector of the external forces. Q is vector of the distributed forces distributed along the finite elements. Quantity of concentrated forces Q equivalent to distributed external load on the rod finite element in projections in the Mathcad, and the distributed loads Qx and Qy is indicated on the figure of the page of the Mathcad, fragment of the page of the Mathcad. So first is the set of the external load of concentrated one. We have assigned the load applied to the up and left one node of the mechanical system. So look here. Oh, excuse me, I have no here. The I have no definite one file. I'll let me show on the page of the Mathcad, the scheme of the mechanical system. So we have the scheme. We have the load applied to the node 2, rightward applied the force P1. We set this as a force P, and we assigned that vector of the forces, which is the forces elements of the vector of forces are the forces in the same directions in which we are looking for the displacements acting in the on the nodes of movable nodes of the mechanical system. So now, considering the discrete model of the mechanical system, we have to find the displacement of nodes. The node 2 horizontal displacement delta uppercase letter 1, the vertical displacement of the same node 2, this delta 3, and the angular displacement of the bending of the rigid corner 2, the displacement 2. In accordance to that, excuse me, delta 3 is the bending displacement angular, and delta 2 is a vertical translational displacement of the node 2. And we as well consider two displacement of the node 3, so horizontal displacement delta 4 and delta 5. This is a vector of the displacements of the nodes of the discrete model. Corresponded to this vector of the displacement as well, we consider the vector of the external forces. External forces, we have only one assigned to the horizontal force applied to point 2. The force is F1, parallel to the abscissa axis X. And we, to use within the Mathcad method, have to consider the forces applied to all of displacements. In the displacements of the this node, we have two displacements because the rigid corner, and this we have two displacements because this is the hinge joint. So this for the node 2 we have three displacements subject to find. So in the same directions we consider the elements of the vector of the external force, but the first component we have assigned F1 50 kilonewton. That all other components are zeros. Formally they are, but are zeros. And besides, zeros of the set of the external load applied, concentrated external load applied to the nodes. But we have distributed load, so we have to consider as well the impact of the distributed load, and to reduce the distributed load to the concentrated one applied to the nodes. So we have the vector of 5 components. This first one component is assigned horizontal force 50 kilonewton to the node 2. 5 components, the same 5 in the same one sequence as the displacement subject to find. So the second one, force 0, but this is applied the vertical force F2 applied to node 2 in the same direction than second displacement of this definite one node. And the third component of the force vector F stroke transposed vector is the transpose description is 0, because so this the bending moment applied to the point 2 external, we have 0 bending point applied. So we just consider like the availability of the definite one component of the external load as a bending moment concentrated applied to the node 2, but we assume that the value of this the magnitude of this moment bending of the node 2 have to be equal to 0. This is because this bending moment is not assigned. This is a formal set of the concentrated external efforts assigned to the considered a show decision of the statically indefinable frame. So to the node 3 we have 2 components of the force applied. One horizontal component have to be is equal to 0. I mean applied component. Besides of that, we as well have the distributed load, and we will look for the concentrated force when we reduce this distributed load to the nodes and with them to the node number 3. Yeah, we will do that. And besides, we will consider the distributed load on the node 2, 3 as well, and reduce the distributed load to the concentrated efforts applied to the node 2 and node 3. But actually, to the node 3, we have 0 concentrated forces applied as the initial data. So we assume 2 zeros forces of 5 components in the same directions than the displacements of the node subject to find by the finite element method. So let me go back to the presentation of the article 4.11. Okay. So we have the same fragment of the Mathcad computer algebra system page. Yes, and next we have to specify the vectors of the distributed load over the elements, finite elements of the discrete model of statically indefinable frame. The elements, the vectors of the distributed load in the projections on the abscissa axis and in projection on the ordinate axis, we have consistent each of 4 elements. For this, just because we consider these elements for each of the finite elements. So we have 4 finite elements. The first finite element between the nodes 1 and 2, the second finite element between the nodes 2 and 3, the third finite element between the nodes 3 and 4, and fourth finite element between vertical stand between the node, the hinge 3, and the fixed hinge of the support 3 and 5. So we have 4 finite elements within the considered statically indefinable frame. And in the general approach, we have the external distributed load acting on these elements could be 0. Magnitude of the distributed load, yes. If we have the distributed load, we indicate 0. So we, for the first finite element, we do not have the distributed load, so we indicate that the magnitude of the distributed load is 0 in the projection on abscissa axis, the same on the projection on ordinate axis. On the second finite element, the horizontal beam between the nodes 2 and 3, we indicate the element magnitude of the distributed load Qx in the component projection of the distributed load acting on the second finite element. Projection of the horizontal axis x is 0 because this definite second finite element does experience the distributed load, but in the vertical direction. This is downward directed distributed load acting on the second finite element, and this is assigned -20. The third finite element is the inclined. We have the assigned components of the distributed load acts even by the length of the inclined finite element number 3 between the nodes 3 and 4. So the one is equal the magnitude of the distributed load projection on the abscissa axis -12 because the distributed load directed to the left, otherwise that the direction of the abscissa axis is to the right. So we have the -12, the magnitude of the distributed load in the projection on the abscissa axis acting on a third finite element. On third finite element, the projection of the distributed force on the ordinate axis, vertical axis, -16 because we have the distributed load directed downward on acting on third finite element. But magnitude is equal to 16, but the ordinate axis is directed upward. So and the 0. 0 is the distributed force acting two components, horizontal component Qx and Qy of the distributed force acting on force finite element, the vertical stand between the nodes 3 and 5. The same 0 distributed load, the same as for the action of the distributed force on the vertical stand between the node 1 and node 2. So the first finite element, we have also 0 distributed load. So transformations of the distributed loads we specify here Qx and Qy acting on each finite element. We can indicate the number of the finite element beginning and number of the end of the finite element to the global coordinate system. Global is a coordinate system of axis x and y, which in we have the assignment of the frame in the global coordinate system now. And this is a more general approach. The finite element indicated on figure 4.10.1a, only 4.10.1. Oh, sorry, probably the wrong number of the figure. Global system coordinate to the nodal load. So we are talking about the reduction of the distributed load acting on each finite element to the nodal load, which corresponds to opposite directions of the reactions P1, P2, P3, P4, and P5, and P6. That is concentrated forces which are equivalent to the distributed external load. So in the more general approach, we have the scheme of the finite element, Rho finite element, which consists of two ends, end number I and end number G. In the general state, if we assume perhaps that the ends of the finite element are rigidly connected to other finite elements or are embedded to the supports, we have the bending moment action at the end of finite element and the horizontal force parallel to the abscissa axis and the vertical force parallel to ordinate axis. And sequence of the indexes of the forces is 1, 2, 3. The same for the second end, we had the bending moment of the reaction of the rest part of the mechanical system or the support. The forces number horizontal one, number P4, number P5, and the bending moment number P6. Besides, we have here the sizes of this finite element, the projection on the abscissa axis we have the angle of the inclination of the finite element to the positive direction of the abscissa axis, and we have directions of distributed load positive. So we have distributed load directed upward, so we have the positive direction, and coincides with the direction of the ordinate axis, and if we have the distributed load applied rightward, we have the positive direction, because direction coincides with direction of the abscissa axis. This is on the figure 4.11.2. This is just the general scheme how we assume the finite element and what is the forces, the sequence of the indication of the forces and efforts, and not only forces but the moment action on the finite element on the beginning of finite element I and the end of the finite element G. The efforts subject to find of the finite element. It could be the zero magnitude, for example, if we have the hinged connection, so we will have zero the bending moment just only, but the general scheme, the most general scheme of the finite element, road finite element, will be the same, just only with zero magnitude of definite one effort acting on the finite element. And due to the formula of determination of the vector of the external load acting in the on the nodes of the finite element, because one of the assures we have to do originally to use the finite element method when determining the efforts in the finite elements of the mechanical system, we have to find the total of two vectors: vector of the external forces and vector of the external forces applied concentrated to the nodes of the mechanical system, and the vector of the concentrated load which we adopt to the nodes of the mechanical system instead of the distributed load of two components qx and qy parallel to abscissa axis and to ordinate axis, distributed loads which correspond to the not to the nodes. This is for the nodes of stroke, and q the force with the components applied to the nodes of the mechanical system of the discrete model of the mechanical system. But this is the vectors of the distributed load correspond to the elements of the mechanical system, not to the nodes, but to the elements, and the nodes are just beside the element, and the elements are the rods between the nodes. And this is the on the figure 4.11.3. the direction was about the same to scheme A and B of the finite element, and the direction of the concentrated load applied to the finite element, the beginning and the end, in our definite one case, because of this is the node number 2, this is the node number 3. So as in the node number 2 we have rigid corner. For the rigid corner we have the bending moment, F3 stroke. F3 stroke means that is assigned as the concentrated moment. This is assigned with the magnitude of 0, because we have only assigned the horizontal component of the 50 kilonewton concentrated load assigned applied to the node 2. This is a node number 2. The force F1 is applied to the node number 2, and the force F2 vertical one applied to the node number 2 upward. And the second and the third node, we have the rigid connection of the finite element number 2, the rigid connection, no rigid connection, but the hinged connection, and hinged connection can transmit just only the translational forces. The forces like F4 stroke horizontal one component of the force applied to the end of the finite element, and the upward component of the force applied to the second node of the second finite element. So it do not correspond the bending moment, so we have only 5. The 1, 2, 3, 4, 5 elements of the external force applied to the third finite element at the directions of the components of the force at the end of the finite element. Applied force coincides with the direction of the displacements available of the nodes of considered nodes of the considered mechanical system. So the node of the region connection we can consider as the corresponded with the vector of 3 displacement, horizontal displacement of the second node, vertical displacement, second node, the bending displacement. And for the hinge, subject of definition is a horizontal displacement and vertical displacement because the hinge do not transmit the bending moment. And the same, we have to find the components of the distributed load acting in the finite elements of the discrete model of the considered mechanical system. But we have to reduce the distributed load to the forces applied to the beginning and to the end, to the first and to the second end of the second one node. And we have 5. We have 5. 1, 2, 3. 3 is a bending moment, is not a force. 4 and 5. The efforts caused by the action of the distributed loads on 4 elements of the mechanical system. So we have 4 elements of mechanical system, and for the movable nodes, available to move the nodes by the deformation of the mechanical system, we have 5 components of the displacement available. And what is the components of the concentrated load to which we reduce the distributed load action in all elements of all 4 elements of the mechanical system? We have reduced to 5 components applied to the node second and the third node of the mechanical system. That is the nodes in which between is the finite element number 2. In a more general approach, for 6 elements of the 6 components of the this 6 components, 1, 2, 3, 4, 5, 6 components. Not as for our mechanical system, we have only 5 components for the mechanical system, but in the general approach, for the arbitrary any one finite element of the mechanical system, we consider 6 components. And for these 6 components, we can find under action of the distributed load, the if this finite element we assume is loaded by the vertical distributed load, positive here in this definite one scheme, and positive here of horizontal component coincided with the direction of the abscissa axis in the definite one scheme. For this scheme, figure 4.11.2, we can find the standard decision. What will be the support reactions equivalent to the considered components of the ends of the efforts acting at the ends of the finite element mechanical system. So the under action of the horizontal force Qx acting on the length of Ly, so the horizontal component acts on the vertical component of the mechanical system. So let me again come to the Mathcad. Yes. So, for example, the horizontal component of the distributed load acts on the definite one, including finite element number 3 in considered mechanical system. But it acts at any point of the considered component of the finite element of mechanical system. And to find the force and action of this distributed load, we have to consider the length of the span of the action of the distributed load equal to vertical component. So the force is parallel, but the opposite direction to the abscissa axis, but the length of its action equivalent to projection of this inclined definite one element of mechanical system on of we have to product this distributed load by the vertical projection of the inclined element of the mechanical system. This is understandable. As for the vertical component with index, with the index have to be qy because directed parallel to the ordinate axis, but to that direction, so with the minus sign. But to find the force, we have to find the product of this vertical component on the horizontal component of the length of this inclined element. So we product the horizontal component of distributed load on vertical component of inclined element of the mechanical system. And we have to multiply the vertical component of the distributed load on the horizontal component of the projection of the inclined element of the mechanical system. What we do in the standard decision in the considered in the presentation system of the equation. I go again back to the presentation. So we have to multiply the magnitude of the vertical distributed force on the projection of the inclined element mechanical system in the general scheme, general for any elements of the mechanical system, not only for the considered one system. So multiply distributed load by the component horizontal along the abscissa axis, but the distributed force is with ordinate index, and the component of distributed force applied to the right with the abscissa index. We have to multiply by the length of the vertical component with the index y, with the index of the ordinate y. So this is understandable in what direction. Force in the another direction, we have to consider the component of the mechanical system finite element. And for the finite element of first type, let me please remind that we consider 4 types of finite elements of the mechanical system. The first type is the finite element embedded by 2 ends. Do we have this one? Yes, we have in the considered mechanical system. I show this on the scheme of the assigned mechanical system as the first element embedded by the node 1 and connected rigidly to the second element in the node 2. So this is the first type element of the mechanical system. The second type is the element of the mechanical system embedded at the beginning and hingely connected at the end. The third type is element mechanical system hingely connected at the beginning and embedded at the end. And the fourth type of the element of the mechanical system is hingely connected at both ends, single span elements of the mechanical system. That is the types of the finite elements of the mechanical system. So for the first type, we just perform the formulas of 6 components of the forces acting to the ends of the mechanical system. This is not applied to the definite one mechanical system in the considered issue. But this is just how it is for the first type element of the mechanical system. Perhaps if we assume this element mechanical system embedded by both of the ends, embedded if this would be the first element, and it is because we have the bending moment at the end, so we assume that perhaps this element of mechanical system or is embedded by the end or is rigidly connected by both of the ends. And we have the formula. The formula is very easy, understandable. Distributed load multiplied by the acting horizontally multiplied the component of the length of the action, vertical component of the action divided by 2. This is the force at the first end, the horizontal force, because the distributed load with the index x, the distributed load with index y, the vertical force at the end of the finite element of the first type and the action of the distributed load vertical is minus the fraction in the numerator. We have product of the distributed load magnitude acting upward multiplied by the horizontal component of the length of the finite element divided by 2. This is understandable because this, if we do have the total of these two components, we will have the total projection of the distributed force even distributed and equally distributed between the supports, the force of and this is the moment. The moment is considering sine of the angle of the inclination, sine and cosine of the angle of the inclination of the component of the force acting on the length of the in the perpendicular direction length to the direction of the force, and multiplied by L by sine alpha, because we have to consider action of the inclined of the forces on the inclined element of mechanical system, and this is the same but under the action of the distributed force in the vertical direction on the size of the system, horizontal size of the system, horizontal projection, and the same by the arm of the action. This is a moment. This is a component thought indicates a moment. So this is like a P3. So this is P1, P2, P3. P1 is the force, P2 is the force, P3 is the moment. So P6 in the standard decision for the finite element of the first type is minus P3. That you can see that the same, but with the minus sign, with this minus, this plus, this minus, and the force components are the same as so under action of distributed load, the force P2 equal to P5 and P1 equal to P4. This is in a more general approach if we consider the finite element of the first type and the action of distributed load with two components, horizontal component Qx and the vertical component Qy. For other types of the mechanical systems, if not the first type, is the second type, finite element of mechanical system could be embedded by the beginning and rigidly connected by the end. We can find in the internet directories and the databases as well the standard formulas of how to find under the action of distributed load, the beforehand decision how to find the support reactions, support the translational reactions, and the bending moment at the end. And we consider 6 elements because if the distributed load do not cause the definite one component of the support reaction, we just define this as a 0 component of the support reaction. But in any case, the size of the vector of the support reactions we consider as consisting of 6 elements for the rod finite element. The first and force is first and force is the projection of the end forces of the finite element here on the of the distributed load. This is the external forces. This is side, and this is as we have in definite hour considered a show. But this is a scheme for any general approach. What is a general finite element scheme, and the forces could be some of the efforts to the ends applied are zeros, and the cause of these efforts appearance is the distributed load. So distributed load is assigned, and these forces we have to find corresponded to the assigned distributed load. Yes, and if for all 4 types of finite element we have the same formulas, if we will find the same formulas for all 4 types of finite elements, these all 4 types are available in our mechanical system. In our mechanical system we have the first type finite element, the rod number 1, the second type as rod number 2, the third number type, the finite element hinged by the beginning and embedded by the second end as the finite element number 3 in our consideration. And the finite element of fourth type is the finite element of in our show mechanical system considered in our articles 4.10 to 4.15. We have the fourth type of the finite element, the fourth definite one rod of the mechanical system. It's not mandatory. Perhaps in some issues could be the other sequence. not mandatory, the correspondence of the types of finite element to the number of the finite element. This is only for our issue. Is for our definite issue. The first number of finite element is of the first type. The second one is number of finite element in our mechanical system is there was a second type, etc. It could be another sequence, and in the general approach, it's arbitrary. But for any type of finite element, we have to find from the directories, from the database internet, from the textbooks, the formulas available to find the support reactions. In the general approach, there will be 6 support reactions, although some of them could be zeros. So for hinges, for example, the bending moment in the support under action of when the element is under action of the distributed force. But the bending moment could be zero if we have the hinge connection to other finite elements in the mechanical system or to the supports. Okay, so besides of that, we have to have the simplification, as if we consider very attentively the we can find the magnitudes. The magnitudes common for the elements of the mechanical system. So, for example, the magnitude of the Qx product by Li. We can find here. We can find here in the definition of the element of the bending moment and the support. If the element is under action of the distributed load, we can find here Qx by Ly, etc. Ql x by Ly here. Yeah, and we can allocate this as a separate function, and this simplifies the description of the action in the Mathcad computer algebra system over the to find the support reactions. We can simplify the description of the finding of the vector of the support reaction vector for the first type. Here we have so the first simplification is the assigning that the vector, this vectorization option, this we can do when we have the product of 2 elements of the 2 magnitudes in the Mathcad computer algebra system. We can access the Mathcad panel. In the panel, we can find the matrices and actions within matrices. We can use the operation of the vectorization. This is used to define the magnitude defined here. Here we magnitude v. Magnitude v is just a designation. We assign this assignments on shift columns. It is not equality, it's assignment equal to product of 2 functions. And we access next. We select by the mouse this product, and we access to the Mathcad panel and to the operations with matrices and vectors, and we can use the vectorization, the operation over the product of these 2 functions. Why we do that? We do that as to consider in the next the v magnitudes as the elements of vector. So this is v with the index y. The variable y means that this is element of the vector v. But to do that, first we have to assign v the definite function and the concept of the vectorization. That is why v is vector in the Mathcad computer algebra system. The second simplification is assigning to the w designation symbol of w assigned shift columns the product of the horizontal component of distributed load by the vertical component of the length of the finite element, definite one finite element, and we as well assign the vectorization, within the definition of the vectors of the end reactions. We have 6 we have four elements of the considered mechanical system. We have 6. 1, 2, 3, 4, 5, 6 elements action in the vector of the support reaction and action of distributed load in the mechanical system. We assume the distributed load. We specify this in the functions and the common functions for all the elements, or for many elements. Next, we just use the symbol of the element of vector of the W to do the W as vector with not definition of the range of the W elements. Before we not do that, we can just select this function and to access to panel of the Mathcad computer algebra system and to access the operations with matrices and to define for this product the vectorization operation. So, and the function u as well, we assign shift columns. We assign the this is for the definition of the elements of the numerator of the support reaction, the end. We do not say the support reaction. Perhaps this is not support. Perhaps this is just the ends and the connection of any one finite element to the adjacent finite elements. Maybe not support. So the more correctly to say that this is the end efforts, not support reactions components of P, but the end reactions component of P. The third one is moment. If it is, or if it is not, just could be 0 here. Anyway, we have 6 as each end in the flat approach for the flat rod frame, as we considered for the each finite element, we have considered 6 available displacement. This is, I'm sorry, this is 5 displacement of, in our definitely consider it as sure. But in a general approach, we have six elements, 6 displacement of each end of the element in the mechanical system. In the global coordinate system, this is 6 elements. Six elements, yes. 1, 2, 3, 4, 5, 6 elements of the forces corresponding to 6 elements of the displacement of each end of the element of mechanical system. This is a definition for the finite element of the first type. What is the magnitudes and dependence on distributed load of 6 end efforts. The third and the 6 is the efforts of the as a moment, as the end moment section under the action of the distributed load. The end moments arises 2. So, and they are like the product of the force on the arm, and the arm is the length of the definite one element, not the projection on the ordinate axis, but the length of the definite one element by the sign of the angle of the inclination of this definite one finite element to the positive direction of the abscissa axis. So, and after this simplification, for our considered assure, let's please determine using the Mathcad computer algebra system the vectors of the end reactions rising under action of distributed load. So we have to find that because the final goal is to find the second summand in the definition of the vector of the external load in the process of reducing of the load to the application to the nodes of the discrete model of the mechanical system to use for the calculations within the Mathcad computer algebra system. So besides of this one formulas, we have to have 3 more options. The second option about the same formulas, but a little bit different one with other coefficients using the standard decision for single span rods. The decisions available in the internet under the action of the single span rod of the distributed load, even distributed load. We can find the same formulas for the end forces and for the end moments if the rod is under action of the distributed load and if the rod is of the second type embedded by the left and hinged by the right, or the third type hinged by the left and embedded by the right, or the fourth type, the element hinged by both ends. So in any case, we can find the sequence of 6 equations for the standard decision of the even distributed elasticity along the rod, the the elasticity and the load even distributed along the rod. And having that, we can go to the Mathcad. And this is for the rod of the first type. So the formula in the Mathcad for the definition of the n directions acting if this definite one rod of the first type embedded by both sides, if it is loaded by the distributed load with, in a general approach, two components Qx and Qy. And this is 1 second. Here, for the beginning moment, we have the factor 1 to 6, 1 to 6 with a minus sign as well. And y 1 second? 1 second we derive out of the brackets of the vector of the n directions 1 second. And 1/6 remains here. If we remove m 1 second, only remains the product of the qx by the ly, the horizontal distributed load to the vertical size of the finite element, vertical magnitude of the distributed load by the horizontal component of the finite element. This is the same indexes here and symbols here, and divided by 12 if we take out of the brackets just the fraction 1 to 2, 1 second, 1 second, yeah, then we have here just numerator remains in the element of the vector, and the numerator divided by 6. So that's what we have, numerator divided by 6, numerator by 6, and we as well account the signs. The third, fourth, fourth, fifth, and sixth elements are about the same one as the previous, but the fourth is with the same sign, others is of the other sign. So this is a projection of abscissa axis of the same sign. This is the projection of ordinate axis with the other sign, and etc. So next we can check what is the definition. In our case, we have the first finite element with critical stand is of the first type. The first finite element P1 means that the element is of the first assigned this magnitude. How we determine that? The formula, the function, independence of the number of the finite element. It is the first finite element is of the first type embedded by both sides, but we have all zero magnitudes of the elements of this vector y, because the first finite element is not under the action of the distributed load. So we have zero, so the n directions of the fourth finite element. About the second finite element embedded by the left, to be honest, not embedded, but rigidly connected to the first element by the rigid corner, to the vertical stand, rigid connection. And it is of the definite sequence of the n reaction. We have the distributed load. Distributed load is we have, as I remember, 20. Maybe let me please remind that I go again to the Mathcad. Yeah, we have distributed load by 20. We have distributed load 16 vertical component action on the third finite element, and we have horizontal component minus 16, minus 12 acting on to the left on the third finite element. So, and to the right we have applied force of 50 kilonewtons. So, come again to the presentation. And we have zeros because the first stand do not experience the distributed load, second experience the distributed load, and we have the forces acting under the action of distributed load. The formulas of here is of the same type like the formulas for the first finite element, but we have to find for the second one the same formulas to specify. This these formulas found and specified already. So if we will consider the common functions here defined before the definition of the components of vector of the end load acting due to the distributed load action on each finite element. We using these factors like -5, -5, 1, just 1, -3, -3, 0. We can find the magnitudes of efforts, that is the forces, 0, 15, -40, 0, 30, 0. The forces acting on the second finite element are the action of distributed load. We have the projection of the horizontal force acting on second finite element equal to 0. Why? Because we do not have distributed load in the horizontal direction acting on the second, the horizontal finite element between the nodes 2 and 3. And that is why we have no the horizontal component of the end force acting to the end of the second finite element at the node 3. So by the same by the same reason as we have no horizontal distributed load acting on the second element, and we have -40, -40, and 30. This is -40 is a bending moment in the connection of the second type finite element of the embedding. This is the moment, and the 50 and 30 is the two vertical forces at the ends of the second finite element. It's understandable because together we have 80. What is the distributed load of the magnitude 20 by the length of the finite element 4 meter together by the length gives us 80 total force acting to the second finite element in the projection on the ordinate axis, and distributed like 50 to the embedding and 30 to the end. Okay, so the finite element of 4 type 0, 0, 0, 0, because the fifth finite element do not experience external load. Exactly, we have the standard decision as of the same function, use elements of the same function within the vector of the forces action in the if there would be the distributed load. So we can find by this formula, by this function, but the finite element V, the definite one formula is of the force type. There will be zero moment corresponding to zero moment at the hinged supports of the finite element of the force type. And again, about the third type, this looks about the same as the element of the second type. The second type embedded at the beginning and hingely connected at the end. The third type hingely connected at the beginning and embedded by the end. We can see that the elements of fourth, fifth, and sixth element of the finite element of second type corresponds to the third type as first, second, and third elements. That's why, because we have the hinged connection at the end of element of the second type and at the beginning for the element of the third type. And we have the embedding at the beginning of the finite element of the second type. And so the first three components of vector of the n direction is -5 by v, -5 by w and u. This is the same as we have here, but with the another sign. It could be just a little bit mistake, but it's not a big deal because we subtract from 0 of definite magnitude u, like here we just consider with a plus sign, etc. So let this is the bending moment minus u bending moment, like here u, the minus u is the bending moment. Let's go to the Mathcad again. We can correct this a little bit, just remove 0 from here. It's not a big deal. Okay. Oh, no, excuse me. It was good. Yeah, it was a good decision. 0 minus this, the magnitude s. Mhm. Go back to the presentation. Mhm. Okay. So, and after the definition of the end reactions, we next can go to determination of the the vector of uh, the reduce of the distributed load to the node forces. So we have 1, 2, 3, and 4, the concentrated forces due to action of the distributed load. This is a vector of the forces in the directions of the displacement subject to find of the nodes of the discrete model of the mechanical system under the action of the distributed load assigned to our mechanical system. So as to the first element of mechanical system, we have no assigned load, the same as to the force, we have zeros as well. And we have the concentrated forces on the longitudinal force acting in the second node, horizontal. The horizontal force, I'm sorry, not longitudinal, but horizontal force, vertical force. This is the same as of the end forces acting on the elements of the mechanical system, but with another sign. So we have the plus, minus, 0, 30, 0. So we have minus, plus, 0, and minus. So instead of 1, 2, 3, 4, 5, 6, we consider only 5. Why 5? We consider defining the elements of the concentrated forces. Hence, we had the 6 elements of the end loads, because the elements of the end reactions we have 6 due to the the most general scheme of the finite element. We have 6, 1, 2, 3, 4, 5, 6 forces acting in a more general approach. What is the finite element, the root finite element? We have to have 6, but in our considered issue, we have only 5. As at the second, the third node, we don't have the bending moment. This is a hinge connection. This is embedding this hinge connection. So we reduce for one component. We don't consider 6, we consider only 5. And we change the sign because the concentrated force acting at the end of the at the end of the finite element, if the finite element is under action of the distributed load, the concentrated force transmitted to the node of the discrete model of the mechanical system will be of the another sign. This is opposite force to the end force acting in the finite element. So we have to change the sign. We have 0, 0 of the 5-component vector of the forces acting in the nodes which displacements are subject to find. We have 5 displacements to find. For the node 2, we have 3 displacements, 2 translational and horizontal, vertical, and 1 rotational of the node of the rigid corner 2. And we have only 2 displacements subject to find of the node 3. Because this is a hinge with not the bending, we consider only the translational displacement, the horizontal and vertical 1 displacement. So together we have to consider 5 displacement. It is subject of our interest of the forces acting in the nodes under the action of distributed load. So the action of distributed load we consider on all 4 finite elements. How this corresponds to the components of the concentrated force acting in the displacement subject to find by the decision of the finite element method. So we have 4 vectors of the influence of the distributed load onto the the node forces acting on the discrete model of the mechanical system. The force is 0, so the force through do not imply on the forces acting to the nodes, not applied on the concentrated forces acting to the nodes in the directions of the displacement subject to find. The stand number 4 in the mechanical system hinged by both ends and not experiencing the distributed load, no impacts on the forces acting on the movable nodes of the discrete model in the directions of the displacement of the nodes of this one subject to find directions displacements. And this is the influence of the distributed load acting on the second element between the node 2 and node 3 of the mechanical system. Second finite element. This is the vector of the concentrated efforts. The first is the force, the component of force, under the action of distributed load applied along the to the node applied to the node 2, the left end of the second finite element. This is the moment in the rigid corner between the first and second element. This is 0 of the horizontal force action on the horizontal direction to the second end of second finite element between the node 2 and node 3. This is a force directed upward, the component of the force projection on the ordinate axis, the hinged connection in the direction of the fifth displacement of the node of mechanical system subject to find. And this is forces acted in the directions of the displacements of the nodes of the discrete model, the direction subject to find the 0, 0, 0, and the third is the horizontal force acting on the node number 3 on behalf of the force distributed on the finite element number 3, inclined finite element of the length 5 meters. And this is a force component vertical, the last one, force vertical component, acting in the node number 3 with a minus sign, but to the assumed direction of the displacement upward of the node number 3. This minus sign means that the force acts downward on the action of distributed load on the finite element number 3. How it corresponds to the forces coincides by the directions with the displacements of second and third node of the discrete model of the considered mechanical system in the directions of the available displacement of the nodes and the action of the distributed loads which are on the third finite element. So this is sounds a little bit complex, but not a big deal. And with a minus sign, considering the got magnitudes, with not the last one, -6, it is the end direction of the embedding of the third finite element, because finite element number 3 by the beginning hingely connected with the elements number 2 and number 4 on one hand, and on the other hand the infinite element of number 3 embedded by the second end to the support. So it's -6. We don't consider the displacement of the support is 0. Support is impossible to displace. So after that, we have to find the all concentrated forces acted on the nodes of the mechanical system instead of the distributed load, which acts within a definite one finite elements. We have the distributed load acting on the second, on the third finite element. This is a total. We assume that all the forces are opposite to the end reactions got by the standard decisions for any of the 4 type finite elements, we assume the simplification of the description as a common definitions as the functions we derive out of the definition of the magnitudes of the end forces. As the vector components, we defined it before, the forces and the moment u, and we define the end forces, and after that we find what is the we found what is the end forces opposite to the what is the end reactions, and reactions opposite to the end forces acting under the distribution of the load, under the distributed load. And finally, the concentrated forces acting to the nodes of the discrete model of mechanical system, we find as a total of f stroke plus q. F stroke we defined originally here, as we have f stroke vector transposed is 50, 0, 0, 0 is a force assigned applied to the node 2 parallel to opposite axis directed right to the right. So we have find all the vector of the forces if we by the forces substitute the action of the concentrated force assigned in the exercise, and the forces which we can determine as a substitute of the distributed load within the element of the mechanical system. So one of the main issues when we use the Mathcad computer algebra system and the finite element method, we have to reduce the action load to the nodal load. This is a reuse of the of all loads applied to the nodes and applied within the finite elements as attribute load. This is reduced to the nodal load, equivalent of the assigned load to the finite elements of the considered mechanical system. So questions and comments. The action of reactions on each finite element at the joints with other finite elements or with the support, which are equivalent to, in the magnitude to the total distributed and concentrated external load action on this element and are opposite to this load. Yes, it is. We consider separately finite elements and assuming the type of finite element, one of 4 types, and assuming the availability of the absence of the external load acting on the finite element, and we find the end reactions of finite element we found, and we next found the equivalent length and the magnitude to the total distributed and the concentrated external load, the forces applied to the nodes in the supports of each finite element, but this is the nodes of the discrete model of the mechanical system. 4.11.2. Setting the distributed load acting on the frame using the finite element method and the Mathcad, and converting the distributed external forces to nodal forces, the number of which, like the number of concentrated external forces, correspond to the number of degrees of freedom of loose nodes. Yeah, we one of the assignment within use of the Mathcad and the finite element method is the setting the distributed load to the converting the distributed load to the concentrated forces, and we have to convert distributed external forces to the nodal forces. This is the main issue. One of the main issue, because we have to have the factor of the nodal forces. Nodal forces consist of the total of the specified nodal forces concentrated and the distributed load converted to the nodal forces as well. And the total will is giving us the nodal forces required to use a finite element method. 4.11.3. Determination of the vector of end forces from the distributed load acting on the finite element. The formal similarity of the global coordinate system used for compact representation Mathcad and for determining the ends forces from the influence of distributed load on root elements of different types of 4 ones. Yes, we can find the standard decision of the end forces acting for the finite elements of other types within the available directories or textbooks, and using that formulas we can find the end forces, which next we use for the determination of the nodal forces required to use the Mathcad and the method of the finite elements. And these formulas for other types of the finite elements embedded by both ends, embedded by the beginning and hinged by the next end, and embedded by the hinged by the first end and embedded by the next end, or hinged by both ends. The formulas are of the number of the similarities. We can find the similar factors predefined before the use of the formulas for finding of the components of the end reactions of the vectors of the components of the end reactions of the finite elements other types and the action of the distributed load. This simplified the specification of these functions in the Mathcad. We have as well use a vectorization operation as well within the opportunities available in the Mathcad in the panel of the Mathcad in the panel matrices vectors. We can find the function of the vectorization. This is the simplification of the definition of the end forces acting on the action of the distributed load at finite elements of other types. 4.11.4 forming the set of initial data referring the distributed and concentrated loads to finite element connection nodes as a separate issue prior to the considered method use. This is important that one of the main issues is reducing the external load to the nodes. So the size of the vector of the vectors of the nodal reactions is equal to the number of the magnitudes of the displacements, number of the displacements, which is possible when the mechanical system is subject for the deformation. So with deformed mechanical system, some nodes which are not supported, just only the so-called free nodes can move. These nodes, if the nodes move, the displacement can be of the translational type, like along the abscissa or along the ordinate axis, or can be a rotational type, like bending rotation of the rigid connections of the finite elements within the discrete model. So, and we have to decide the vectors for the vector geometry using the algebra to decide the finite element method, and we have to describe the initial data like vectors within the approaches of the vector geometry. And within the approaches of the vector geometry, we have to find the number of the elements in the vector of the data. The number of the elements of vector of data of the external force have to be corresponding to the number of the maybe a degree of indefinability or of the mechanical system, or with the number of the displacement available subject to find by the displacement of the discrete model of the connection of finite element into the mechanical system. The displacement, in our case, we consider 5. So the vectors of data initial is of the 5 components. Otherwise, then the finite elements we have 4, the nodes we have 5, etc. So we have to be very attentive to definition of the numbers of the degrees of freedom and the numbers of the components of vectors of the initial data, like the vector of the external forces. 4.11.5 methodological features of referring distributed load to the connection nodes to finite elements associated with the ratio of the number of finite elements and the supports of mechanical system, as well as with variety of types of the finite elements and the forms of their connection in the mechanical system. The end forces in the finite element depends on the availability of distributed load acting on the definite each of the finite element of the absence of the load. If the load distributed is absent, that is it is, but of the zero magnitude. In the formal specification in the Mathcad approaches and the within the finite element method, and the number of support of mechanical system and the variety of types of finite element, we have to consider finding the bending moments, the end forces, etc. We can use the standard formulas got from the directories and textbooks, and to do that, we have to decide what type of the finite element we consider. In definite one case, we consider the exercise. We have all 4 types of the Rod elements of the mechanical system, Rod finite elements, and consider the show of the decision in the Mathcad by the method of finite elements. Let me just go again to the Mathcad. Yes. So, okay. This is finding of the vector of the concentrated loads applied to the nodes of the mechanical system, to the movable nodes in the directions of the available displacement. We have 5 available displacement. Of the node 2, we have 2 translational displacement along the x-axis and along the ordinate axis in the same directions. We consider the applied load by direction of the assigned load and the direction of the external load distributed, and the 2 directions of the displacement of the node number 3. So we have 2 forces, and the action of the distributed load on the second finite element and third finite element. Second is between the nodes 2 and 3, and the third finite element between the nodes 3 and 4. Thank you.